In this video, we're going to talk about basic rules of differentiation. Our objectives will be to answer conceptual questions involving rules of differentiation, to find derivatives using the basic rules of differentiation, to find higher order derivatives of functions using basic rules of differentiation, to simplify algebraic expressions into forms in which basic differentiation rules apply, and to use derivatives to find slopes and equations of tangent lines. Specifically, we're going to need to use the point slope form there most of the time. And just a note here, memorizing these rules or these formulas is preferable to using the limit definition. Every time, right? And we already saw a couple examples last time where we didn't want to use the limit definition because the function was more complicated. These basic rules and some of our extensions of these basic rules will help us to calculate derivatives such as those. So again, coming back to our notation here, y prime or f prime of x. This is our prime notation for our derivatives. We can also take the derivative to be these straight back d's like that. This is the differential operator like this. Is the same thing as df dx or dy dx. This is our differential notation. Differential notation is preferred lots of times because it's much more explicit in telling you what you're taking the derivative of and what you're taking the derivative with respect to. If you just say y prime, you have to assume or know that y is a function of x. This is kind of explicit. You know that you're taking the derivative with respect to this variable here. But we are going to want to take the derivative with respect to other variables later that you don't see in the notation f of x. We'll get to that when we get to implicit differentiation here in a little bit and related rates and things like that that are going to be some applications of derivatives. When we do those things, we're definitely going to want to use this differential notation to show people what it is we took the derivative with respect to. Note there's also another notation here with dots. So the one dot above it is the same thing as the first derivative like that. We also have this subscript notation like this, that's dy dx. And that if we have multiple subscripts like this, then that means that we took the derivative twice. Like this, like that. So we will use these notations in other classes coming up. This dot notation gets used sometimes in differential equations. The subscript notation gets used a lot in calculus 3, specifically when we use another type of derivative that doesn't have a straight back d. I mentioned it last time that it has this curly d like that that looks more like the lowercase Greek letter delta. You have some stuff at the end of your textbook for this class that talks about partial derivatives, and is going to use this notation in it. So go ahead and just write that down, that you might need to know the subscript notation. I don't think your textbook is going to use the dot notation at all. But for right now, as we apply these rules, we're only going to use this prime notation and this differential notation in our rules. We're not going to use these other notations right now. They'll pop up later in calculus. All right. First, the constant multiple rule and the constant function rule and the power rule, which the constant function is really part of the power rule, because really any constant is really cx to the 0 power, and I can use the power rule where it's a 0th power there like that. So what does the graph of y equals 2 look like? And what is its rate of change between x equals 0 and x equals 3? So let's go ahead and draw a simple graph of that here. Y equals 2, between x equals 0 and x equals 3. It's going to be a horizontal line here. And I'm interested between x equals 0 and x equals 3. That's the function y equals 2. So we have the point 0.02, we have the point 0.32, and we find the slope. We have y2 minus y1 over x2 minus x1 is 2 minus 2 over 3 minus 0 is 0 over 3 is 0. And so we would see that that would be true for any horizontal line over any interval, that if we have a constant function, c is a real number, then the derivative with respect to x of c is 0, because the slope of every horizontal line is 0. So it does not matter here what this number is, as long as it doesn't contain any x's and is just a constant. Even if it's something like pi, its derivative is going to be 0. So big idea here, like we said, the derivative of a constant is 0. Right? Our power rule for differentiation, we're going to start off with whole numbers, non-negative integers, but really we're going to be able to extend that to any real number here in a little bit, but we're just going to start off with power functions that we know from polynomials. We already saw last time that when we took the derivative of something that was a 4th degree polynomial, we got something that was a 3rd degree polynomial for a derivative, and that's because of this rule right here. You can actually write this down, go back and look at the notes from last time, and see now how we got those derivative functions so quickly without doing the limit definition. So if I have x to the n and want to find its derivative, it's coefficient times exponent here. So n times 1 is n, drop the exponent by 1. An integer is an element of the set. Bold letter capital Z here. To show bold, we do this extra line here. It's not going to be fractional. It's not going to be irrational in any way. It's going to be the whole numbers and their opposites, right? So let's evaluate here. 2 times 1 is 2. Drop the exponent by 1, like that. 44 times 1 is 44. Drop the exponent by 1 is going to be 43. 1 times 1 is 1. Drop the exponent by 1 is 0. Well, x to the 0 is 1. So this is going to be 1. Watch out here, even though I have a power, it's not on x. This is just a good old constant right here. So that's going to be 0. Don't get fooled by that. Just because you see an exponent doesn't mean that it's the power rule. You need to see this variable raised to a power to have the power rule. If you want to know what 2 to the 8th is, it's 256. So there you go. All right, constant multiple rule for differentiation. This can be combined with the other rule to give you what I was saying about multiply the exponent times the coefficient before dropping the exponent by 1. Constant multiple rule says if f is differentiable at x and c is a constant, then if I take the derivative with respect to x of c times f of x, that this c can pass through the differential operator because the differential operator is just a big limit and constants can pass through limits. That'll be c times f prime of x, where the c just sits there as an observer and doesn't do anything. It just gets multiplied at the end. So intuition using limits, y equals c f of x, applying the limit definition of the derivative. We'll get y prime is equal to limit as h approaches 0, f of x plus h minus f of x divided by h. It's going to give me limit as h goes to 0 of c times f of x plus h minus c times f of x over h. Then that c can factor out. Limit as h approaches 0 of c times f of x plus h minus f of x divided by h. That constant multiplier that's out front here can pass through the limit symbol, equal to c times limit as h approaches 0 of f of x plus h minus f of x divided by h is going to be c times f prime of x, where this is the definition of f prime of x. So this negative 7/8 will just sit there times 11x to the 10th. It's going to give me negative 77x to the 10th over 8. This is 1 times 2 is 2. X to the 0 is 2 times 1 is 2. We have 16 thirds times 7 x to the 6th here. And 3 doesn't go into 7. So 6 times 7 is 42. 7 plus 4 is 11. Like so. All right. Sum and difference rule. We'll look at the sum rule first. So our theorem tells us that if f and g are differentiable at x, then their sum or difference, the derivative of f of x plus g of x, or the derivative of f of x minus g of x, is also differentiable at x and will be the sum or difference of those derivatives. So for the derivative of f of x plus g of x, that'll be f prime of x plus g prime of x. And for derivative of f of x minus g of x, that'll be f prime of x minus g prime of x. So let's find f prime of x for the given polynomial here. What we're going to do is a combination of that power rule with the constant multiple rule attached to it, as well as the sum difference rule to find the derivative of each piece, and say that f prime of x is equal to the derivative with respect to x of 3x to the 14th plus the derivative with respect to x of 6x to the 10th plus the derivative with respect to x of x to the 9th plus the derivative with respect to x of a negative 6x to the 5th plus the derivative with respect to x of 10x squared plus the derivative with respect to x of negative 3x plus the derivative with respect to x of 9. So f prime of x is going to be equal to 3 times 14, x to the 13th, plus 6 times 10, x to the 9th, plus 9, x to the 8th, plus negative 6 times 5, x to the 4th, plus 10 times 2, x to the 1st, plus negative 3 times 1, x to the 0, plus 0. F prime of x will be 42, x to the 13th, plus 60, x to the 9th, plus 9, x to the 8th, minus 30, x to the 4th, plus 20, x minus 3. 42, x to the 13th, plus 60, x to the 9th, plus 9x to the 8th, minus 30x to the 4th, plus 20x minus 3. So while we have the rules here for sum and difference that we inherit from limits, note that we do not inherit the product or quotient rule from limits. We'll have different product and quotient rules coming up here in a little bit. So let's take the derivative of the natural exponential function e to the x. This is a very special function in math where it is its own derivative, and that's why we like it. So every point, the y value at that point is the slope of the curve at that point. So we'll throw in with the constant multiple rule and everything else that this is going to be derivative with respect to x of 2e to the x. The 2 will pass through and be the derivative with respect to x of e to the x is going to be 2e to the x. We're going to have derivative with respect to x of 16e to the x plus the derivative with respect to x of 9. 16 derivative with respect to x of e to the x plus 0 is 16e to the x plus nothing is 16e to the x. And then we have derivative with respect to x of 3e to the x plus derivative with respect to x of 16x squared plus derivative with respect to x of 12 over x squared. This is going to be 3 derivative with respect to x of e to the x plus 16 derivative with respect to x of x squared plus 12 derivative with respect to x of x to the negative second. I'm going to bring that up there so I can use the power rule with it. So this is 3e to the x plus 16 times 2 x to the first plus 12 times negative 2 x to the negative third, 3e to the x plus 32x minus 24 over x to the third. If we want to find higher order derivatives, those will be derivatives of derivatives. So assuming y equals f of x can be differentiated as often as necessary, the second derivative of f is f double prime of x is equal to the derivative with respect to x of the first derivative of f with respect to x. For integers n greater than or equal to 1, the nth derivative of f sub n of x is equal to derivative with respect to x of the n minus 1th derivative of f of x. So the 0th derivative is the original function itself. The first derivative we know how to find with the limit definition, and then every subsequent derivative from there on would be the derivative of the previous derivative. So continue differentiating f of x equals x to the 6th minus 3x to the 5th plus x cubed plus 4x squared minus 9 until you obtain a zero derivative and make a prediction about how many derivatives will be required. I think that I need 6 derivatives to get to a constant of some kind, maybe not necessarily 0, but definitely when I take the 7th derivative here, I should get 0 because I should be taking the derivative of a constant. So I think I need 6 or 7 derivatives here, probably 7. So f prime of x is going to be 6x to the 5th minus 15x to the 4th plus 3x squared plus 8x plus 0. F double prime of x is equal to 30x to the 4th minus 60x to the 3rd plus 6x plus 8. F triple prime of x is 120x to the 3rd minus 180x squared plus 6. Fourth derivative is going to be 360x squared minus 360x. Fifth derivative is going to be 720x minus 360. Sixth derivative is going to be 720. And just as we expected, the 7th derivative is going to be 0. And then every derivative following from there will also be 0 no matter how high you go. So we're done. Let's now look at slopes of tangent lines, which is going to be one of our applications of derivatives here. Big idea in calculus, one of the big problems you want to solve is the tangent line problem. So let's write an equation of a tangent line for a graph f of x is equal to 2x minus e to the x over 2. So f prime of x is going to be equal to 2 minus 1/2 e to the x. And we're told to write the equation of the tangent line at the point 0, negative 1/2. That's nice that they already figured that out for us. So we're going to have f prime of 0 is our x value that we're plugging in. 2 minus 1/2 e to the 0 is 2 minus 1/2 times 1 is 4/2 minus 1/2 is 3/2. So we have our tangent line is going to be able to be found using the equation y minus y1 equals m times x minus x1, where our x1, y1 are here. But I also have been given a y-intercept. So I'll show you how to do this with slope-intercept in a second. It's not always the x equals 0 value that we've been given. So I need to just show you more generally that this is negative 1/2 in here. The slope is 3/2. It's x minus 0. So this is y plus 1/2 equals 3/2. And this is just x. So y equals 3/2 x minus 1/2, which would also be correct if we had used y equals mx plus b. We found y to be m was 3/2 and b was a negative 1/2. That would have been easier, but we need to know this point slope form because we're going to need to use that most of the time. We're not always going to be given the y-intercept as our point. So now let's find all points on the graph of f for which the tangent line is horizontal, meaning that the slope is 0 for the last example. So if we have f prime of x is equal to 2 minus 1/2 e to the x, and we want to set that equal to 0, then that means that negative 1/2 e to the x is going to be equal to negative 2, and e to the x is going to be equal to a negative 2 times a negative 2, or e to the x is going to be equal to 4. And then we're going to take the natural log of both sides to get rid of the base of e. That's x equals natural log of 4, which is equal to 2 natural log of 2. And you can approximate that as 1.386. These are both exact answers here. This is an approximation. Go with the exact answer unless you're told to round. So that means that there's a horizontal tangent line with a slope of 0 at x equals 2 ln of 2. So that tangent line would be y equals 2 ln of 2. At would be you'd have to plug the 2 ln of 2 into this original function here to get a y value. And then once you got that, you could use that point and the slope of 0 to come up with the horizontal tangent line there if you needed the equation of it. So let's now look at f of x is equal to 2x cubed minus 5x squared plus 24x. For what values of x does the tangent to the graph f have a slope of 6? So let's find f prime of x is equal to 6x squared minus 10x plus 24, and we want to set that equal to 6 to solve. 6x squared minus 10x plus 24 minus 6 is going to equal to 0. 6x squared minus 10x plus 18 equals to 0. I'm going to pull out a 2 here to make my life easier. And that means that 3x squared minus 5x plus 9 has to be equal to 0, since 2 is not 0 and the product has to be 0. Let's go ahead and see if we can factor this. 3 times 9 is 27. Factors of 27 that add up to be 5. I don't think so, but let's check. 1 and 27, 3 and 9. That's it. So none of those add up to be -5. So we're stuck using the quadratic formula that x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. X is 5 plus or minus root 25, and then I have 27 times 4, 10 minus 108 over 6. So there's no solution to this because this is a negative inside. So there is no point where f of x has a slope of 6. That's what that tells us. And we're done with this video, and we'll come back next time and we will talk about the product and quotient rules. See you for the next video.